Polynomials might sound a bit scary at first, but they are just a special kind of mathematical expression. Think of them like Lego blocks for equations. You take variables like x and numbers. You can add them, subtract them, or multiply them. You can also raise x to a power, like x squared or x cubed. These are the basic ingredients for building a polynomial. It's all about combining these simple pieces in interesting ways. We see simple polynomials all the time in everyday life. The degree of a polynomial tells us a lot about it. It's simply the highest power of x you can find in the expression. For example, if the highest power is x squared, it's a degree 2 polynomial. This is also called a quadratic, which often makes a U-shaped graph. If the highest power is x to the 5th, it's a degree 5 polynomial, or a quintic. The higher the degree, the more twists and turns its graph can have. It's like adding more pieces to our Lego model, making it more complex. The degree gives us a clue about how complicated the polynomial's story will be. So why should we care about these mathematical constructions? Well, polynomials are incredibly useful for describing the world around us. Scientists use them to model the path of a thrown ball. Engineers use them to design strong bridges and smooth roads. Economists use them to understand patterns in financial markets. They can represent growth, decay, oscillations, and much more. Polynomials provide a language to explain complex systems. Their power lies in their versatility and relative simplicity. A really important concept with polynomials is their roots. The roots are the special values of x that make the polynomial equal to 0. Imagine the graph of the polynomial. Where it crosses the horizontal line, those are the roots. Finding these roots is like solving a puzzle. It tells us key points about the system the polynomial is describing. For a business, a root might be a break-even point. For an engineer, it might be a point of zero stress in a structure. Understanding roots is fundamental to unlocking a polynomial's secrets. Now let's talk about a specific type, the quintic polynomial. As its name hints, a quintic polynomial is one of degree 5. This means the highest power of x in the expression is x to the 5th. Quintics are a step up in complexity from quadratics or cubics. They can have more twists and turns in their graphs. This means they can model more intricate situations. For centuries, mathematicians were fascinated by solving quintic equations. It turns out there's no general simple formula for their roots, unlike quadratics. This makes them particularly intriguing in the world of mathematics. The general form of a quintic polynomial looks like this: x to the 5th plus bx to the 4th plus cx cubed plus dx squared plus x plus f. Here, a, b, c, d, e, and f are just numbers called coefficients. The a cannot be 0, otherwise it wouldn't be a quintic anymore. Each term, like x to the 5th or bx to the 4th, plays a role in shaping the polynomial. Some of these coefficients might be 0, simplifying the polynomial. Imagine it as a recipe with up to 6 main ingredients. The amount of each ingredient changes the final flavor or shape of our polynomial. Understanding this structure is the first step to working with quintics. Let's look at a specific example of a quintic polynomial. Consider this one px equals x to the 5th minus 5x cubed plus 4x. Notice something interesting here. The terms with x to the 4th and x squared are missing. This means their coefficients, b and d from our general form, are 0. Also, the constant term f, the number without any x, is 0. This simplified structure makes this particular quintic easier to analyze. It's like a recipe where we've omitted a couple of ingredients. This often leads to some neat properties, especially when finding roots. Finding the roots of our example, px equals x to the 5th minus 5x cubed plus 4x, is quite revealing. Because the constant term is 0, we know x equals 0 must be a root. We can factor out an xx times the quantity x to the 4th minus 5x squared plus 4 equals 0. The part in the bracket x to the 4th minus 5x squared plus 4 can be factored further. Think of x squared as a new variable, say y. So we have y squared minus 5y plus 4. This factors into the quantity y minus 1 times the quantity y minus 4, which means the quantity x squared minus 1 times the quantity x squared minus 4. So, our polynomial is x times the quantity x squared minus 1 times the quantity x squared minus 4 equals 0. This gives us roots x equals 0, x squared equals 1, so x equals 1 and x equals negative 1, and x squared equals 4, so x equals 2 and x equals negative 2. The roots are negative 2, negative 1, 0, 1, and 2. All 5 are real numbers. Take a look at the roots we found for our quintic -2, -1, 0, 1, 2. There's a beautiful symmetry here, isn't there? They are perfectly balanced around the number 0. The distance from 0 to -1 is the same as from 0 to 1. The distance from 0 to -2 is the same as from 0 to 2. This kind of symmetry is not an accident, it comes from the polynomial structure. Specifically, our example quintic was an odd function. This means p of -x equals -p of x, which often leads to symmetric root patterns. It's like looking at a perfectly balanced mobile hanging in the air. Now, all the roots of our example quintic, 0, plus or -1, plus or -2, were real numbers. These are the numbers you typically encounter on a number line. However, polynomials, especially quintics and higher, can also have complex roots. Complex numbers involve the imaginary unit I, which is the square root of -1. If a polynomial has real coefficients, its complex roots always come in pairs. These are called conjugate pairs, like a plus bi and a minus bi. So a quintic could have 5 real roots, like our example, or it could have 3 real roots and 1 complex conjugate pair, or it could have 1 real root and 2 complex conjugate pairs. Let's briefly step into the world of even higher degree polynomials. Consider this degree 11 polynomial qx equals x to the 11th minus x. That's x raised to the power of 11, then subtract x. It looks quite simple, but its degree is high. This means it can have up to 11 roots. Just like our quintic, we can factor out an x. So qx equals x times the quantity x to the 10th minus 1 equals 0. This tells us immediately that x equals 0 is one of the roots. The other 10 roots come from solving the equation x to the 10th minus 1 equals 0 or x to the 10th equals 1. The roots of x to the 10th equals 1 are fascinating. They are called the 10th roots of unity. 2 of these roots are real numbers. X equals 1 and x equals -1. Because 1 to the 10th equals 1 and -1 to the 10th equals 1. The other 8 roots are complex numbers. When you plot these 10 roots in the complex plane, they form a perfect pattern. They sit at the vertices of a regular 10-sided polygon, a decagon. This includes the points 1, 0 and -1, 0 on the real axis. Again, we see a stunning symmetry, but this time in the complex plane. This kind of structure is common with roots of unity. Why is the symmetry of roots so significant? This symmetry often reflects an underlying balance or pattern in the system the polynomial describes. Think about physics or chemistry. Symmetric arrangements of atoms can lead to stable molecules or crystals. In engineering, understanding these patterns can help design more stable structures. If the roots of a polynomial representing a system are symmetric, it might indicate a state of equilibrium. It's like a perfectly balanced seesaw, where the forces are distributed evenly. This can be a very desirable property in many applications. Discovering such symmetries can provide deep insights. The concept of roots also connects to the idea of equilibrium. In physical systems, roots can represent points where forces balance out, or they might indicate energy minimums, which are stable states. Imagine a ball rolling in a hilly landscape. The bottom of valleys are equilibrium points. If a polynomial describes the energy of that landscape, its roots, or more accurately, roots of its derivative, could point to these valleys. When roots are symmetric, it suggests a particularly well-ordered or stable equilibrium. This could mean the system is robust and not easily disturbed. This is crucial in fields like control theory, ensuring systems behave predictably. Polynomials, from simple quadratics to more complex quintics and beyond, are everywhere. In electrical engineering, they help analyze circuits and signal processing. The roots might tell you about the natural frequencies of a circuit. In computer graphics, polynomials define smooth curves and surfaces. Think of the sleek lines of a car or the animated characters in a movie. In economics, they can model supply and demand, or predict market trends. The ability to find and interpret the roots of these polynomials is key. It allows us to solve problems and make predictions based on these models. In conclusion, polynomials are more than just abstract mathematical expressions. They are powerful tools for understanding and shaping our world. Exploring their structure, like the degree or the coefficients, tells us a lot. Unlocking their secrets, especially by finding their roots, gives us crucial information. Whether it's the 5 real roots of our specific quintic, x to the 5th minus 5x cubed plus 4x, or the mix of real and complex roots of x to the 11th minus x, forming beautiful patterns. This knowledge helps us see the hidden order and balance in complex systems, and that is the true joy and power found within these numbers and symbols.